Hey guys, Unit 10 of Stats. We're on Lesson 1. We are still talking about population means, but instead of creating confidence interval for those values that we don't know, we're going to be testing a claim. So this is going to be very similar to Unit 8 when we tested claims about population proportions. If you skipped that, that's a real bad idea. You're going to want to go back through because this is basically just taking that framework that we did in Lesson 1 of Unit 8 and putting on the mean work that we just did from Unit 9. So we're talking about testing a population mean. There is a problem in Unit 8 about a battery company, and they're thinking that this new battery is going to last longer than their old battery. So we have two claims. We're going to assume that the average duration, I guess, for this battery is 30 hours. We're assuming it because it's in the null hypothesis. We assume the null is true until proven otherwise. But somebody's claiming that it's going to last longer. So we're thinking that mu is actually greater than 30. And mu has been defined as the true mean lifetime in hours for these batteries. You always have to check your conditions. Your conditions for performing a significance test about the mean are the same as your conditions for creating an interval for the population mean. So I don't know how that happened. First one is always your random condition. You cannot have inference about a bigger group without random. So the data has to come from a random sample from your population of interest. We got to make sure that the sample can be viewed as independent, which is our 10% condition. If you're sampling without replacement, that sample size must be less than 10% your population size. Also, the newest condition that we hadn't worked with for as long is your normal/large sample condition. It's literally the same as it was when we talked about the confidence interval. So if I tell you the population is normal, awesome, you're done. If your sample size is large, awesome, you're done. But if you don't know the shape of the population and you have a small sample size, you got to sketch your graph to make sure that there's no dramatic skewness and there are no outliers, so that you can basically say it's plausible that this came from a normal population. Otherwise, you can't use any of the T procedures that we go through. So that battery company has this sample. 15 batteries were selected. This was the lifetime of those 15 batteries. We're going to check the condition. So the first condition, again, is the random condition. And I literally just realized that I didn't get any of this prepped in advance. So you get to watch me write all this out. So it was a simple random sample. So I'm just going to denote that that was told to us. That's very important. So deluxe AAA batteries. Then we got to make sure that that random sample meets the 10% condition. We're going to have to make an assumption here. We don't actually know anything about the batteries produced at this company, so we're just going to be building this off the assumption that 15 is less than 10% of all their AAA batteries. Of all the companies. And then the newest one is the normal/large sample condition. If you're looking at a printed out one, which while I'm writing this out, if you are one of the people that are saying you really wish you could have access to paper copies, you can if you call the school. You have to call the high school in advance, say I need the copies for my statistics class. Specify which unit you need because I've been sending them in chunks of units so you can get it that way. And then they should have it right inside the front doors. You don't even have to go in and talk to people or anything. You can go in, grab your copy, and then leave and go wash your hands at home. So in order to check this, I'm going to take our 15 samples. There are lots of ways you could check this. Remember, you could do a histogram. You could do a box plot, although box plots are not usually the best. I'm going to just throw this on a dot plot because I'm stealing this out of the textbook that I have access to, and that's what they do. So I'm sketching the battery life. This is in hours. The lowest battery life I'm seeing is 17. Okay, so I'm going to count by 5s. And again, you do actually have to sketch it. You can't just say, oh yeah, it's plausible. You actually have to show it if you're going through to meet this condition this way. So I'm just going to throw the data on the box plot, get it approximately close, like there's a 30. It's not perfect, and that's fine. But what you see if you do sketch all this out is there are no outliers. There's not like a dot over here or anything like that, and it's not all bunched up in one section, so it's plausible that this came from a normally distributed population. So I'm just going to put that the dot plot does not show strong skewness or outliers. So check, we met all three conditions. You would be able to go ahead and continue on with creating a hypothesis test for that. So that's what we're gonna do. So in this, if I put those 15 numbers in my calculator, we could find the sample mean lifetime. So as a reminder, your symbol for sample mean is X bar. When I put that in my calculator, I got 33.93 hours. My calculator also spit out the standard deviation of those particular values. Now those are X values, so I'm just going to use S sub X as my sample standard deviation notation, and I got 9.82 hours out of that. So this sample mean is bigger than 30. So there's some evidence that the population mean is not 30. So there's some evidence. We're trying to find, as always, when we do these testing, do we have convincing evidence of this? Do we have overwhelming statistical, not proof, but evidence convincing us this way? So when we do this, we have to standardize this number. So we don't just use this number. We, what am I trying to say? We're standardizing it to measure how far from the sample our sample result is from the null parameter value. So we always assume the null is true, and then we test otherwise. So this is our formula always for the test statistic. The statistic minus the parameter divided by usually the standard deviation of the statistic. When we do this, it's going to turn into the standard error of the statistic. So for some test where the null hypothesis has mu equaling some number, so if that's the format, then our statistic is X bar, so this will be X bar, and the parameter is what we're assuming to be true in the null hypothesis. The standard deviation of a sampling distribution of X bar, we said it's less variable. It's the population standard deviation divided by the square root of our sample size. So ideally, what we would be doing to standardize this test statistic is X bar minus the number from the null divided by the population standard deviation divided by the square root of n. However, you're trying to test mu. If you don't know what mu is, you are extremely unlikely not to know what sigma is. So because of that, because it's almost always unknown, we can use our sample standard deviation in its place. So I'm going to replace this with S sub x. So the resulting standardized test statistic will have the standard error of X bar in the denominator. So instead of the standard deviation of the sampling distribution of sample means, we're going to have the standard error of sample means. And we're going to use T instead of Z. So we're going to change this formula slightly. It's still statistic minus the parameter, but now we are going to be dividing by the sample standard deviation over the square root of n. So it's the standard error of X bar. So for our example about the batteries, to standardize our test statistic, we're going to take 33.93. We're going to subtract. We're thinking it is 30 because that's what's in the null hypothesis. We assume that's true until proven otherwise. And we're going to divide by our sample standard deviation, which was calculated to be 9.82, over the square root of the sample size that was found from which that was found. If you do that correctly, you get 1.55. Here comes a kid to interrupt me, so who knows? Depending on how much she wants to complain about, I might have to just pause the video here. What's up?
I'm going to do something on her list.
You did everything off the list. Go back outside and play. Eloise, I'm trying to make a video now. Go back outside and play, please.
What about this one and this one and this one and
Yeah, you did it all. Go outside and play. Okay, so as long as you've met the normal large sample condition, then you're going to be able to use a t-distribution to model this. And as always, we are assuming the null hypothesis is true. You might find evidence that it's not. You start out assuming that it's true. So, a t-distribution table or the calculator can be used to find our p-values. So we're going to go over both methods. So I'm still using the test of these batteries. So I'm still using these hypotheses. We had a simple random sample of 15 batteries, blah, 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 blah. The p-value is the probability of getting the result that is as large as we got or even larger, just assuming that this is true just by chance. So if we're talking about our symbols for probability, the p-value is the probability that we get an x bar that's as big as it is, so equal to this or even bigger, so equal to 33.93, given that the mean of the population is actually 30. What's the likelihood that we get something this huge or huger if the true population mean is 30? Because it could happen, but how likely is it to happen? So we have our test statistic of 1.55. So that would mean on the t-distribution, which remember looks a lot like a normal distribution, it's slightly different, but we are going to be saying, well, this is our standardized test statistic of 1.55. What's the area of being here or even beyond this? This is our p-value, this probability, this area. So this is the probability that we are getting a t-test statistic of 1.55 or above. So this time, unlike what we did with the confidence intervals, we actually know the number. We also know our degree of freedom. So if you remember, degree of freedom was our sample size minus 1. So that distribution, t-distribution, should be the one with 14 degrees of freedom. So I copied part of the t-distribution table in here. I chopped it up so it actually fit into your notes. But I am only caring about 14 degrees of freedom. Now this does not have every possible value on here. It's very limited. And so I need to look for, I'm looking, why is this not the same? What am I doing wrong? Did I copy the wrong table over? That's annoying. Oh, no, it's not. I can read. Okay, I'm sorry. So we are ideally looking for our test statistic of 1.55. But again, it's not an infinite number of values. There's not every possible area in the tails here. So if you're going to use the table, you're going to be limited. I'm looking for 1.55 on here, and I see 1.76, and I see 1.345. That's as close as I can get on here. So the t-statistic is somewhere between these two values. If the t-statistic is between these two values, then if I look at the top of the table, that corresponds to a p-value between these two values. So the area is somewhere from 0.05 to 0.10. That's what I know. So we can actually go ahead and draw a conclusion here, because we now know our p-value, I'm just going to say it's equal to something between 0.05 and 0.10. I'll show you a way to calculate this later, but I do want to show the table because some people will be forced to do this because of the model of their calculator. So we know this about our p-value. We can still draw conclusions the way we always do. We're comparing our p-value to alpha. So because the p-value, because our p-value of, I'm going to use my shorthand for between, it's a b/t, write out the word if you want to. But because our p-value of between 0.05 and 0.10 is greater than alpha, and alpha here is 0.05, because it's larger than, it's basically saying, oh, this is a pretty common result. This will happen with just sampling variability. So it's not uncommon. We're not going to reject the null hypothesis. We still think that could be the center because this test statistic happens between 5 and 10% of the time just by chance. So because it's greater than that, we are going to fail to reject the null. You always make your decision first about the null because you're assuming it's true until proven otherwise, and we don't have convincing proof otherwise. So we're going to fail to reject the null hypothesis. We don't have convincing evidence that the mean lifetime is more than 30 hours. So that's what I'm going to put here. So we don't have convincing evidence that the true mean lifetime of the AAA batteries, and I'm going to shorthand here because I don't want to write all that out, the true mean lifetime of AAA batteries, of the company's deluxe AAA batteries, blah, blah, blah. So we don't have proof that it actually is equal to 30. We just don't have evidence that it's more than 30. So we'll just keep assuming it is 30 unless another sample convinces us otherwise. So I'm going to stop the video now so they're not gigantic files for me to upload, but example 2 is